Okay, so let's start with theorem 10.7. So this theorem says that if two inscribed angles in a circle intercept the same arc or congruent arcs, then the angles are congruent. So one more time, if two inscribed angles in a circle intercept the same arc or congruent arcs, then the angles are congruent, okay? So let's go ahead and draw a picture of that. So I'm going to again start with my circle. And I'm not going to put my center in there now, okay? What I'm going to first do is I'm going to put 2 points along that circle's perimeter or circumference. And I'm going to start by drawing an inscribed angle to that arc. Okay? So if you notice, that angle, that inscribed angle, is inscribed to this arc right here. Okay? But let's go ahead and draw another angle that is also inscribed to that arc. So now we're almost making like these two triangles, all right? But now I'm also going to inscribe that angle to its arc. And now I'm going to kind of color code a little bit. So I have this angle right here that's inscribed to that blue arc. And then I have this angle right here. So what this theorem is saying is that if you have these two angles that are inscribed to the same arc, all right, then these two angles have to be congruent. And that should make sense to us because if that arc right here is 100 degrees, then using that inscribed angle theorem, then we know that this green angle has to be 50 degrees. And then we know that this pink angle also has to be 50 degrees because it's inscribed to the 100 degrees. And so they would have to be congruent, okay? Okay, so let's practice that. So if we look at example 2, it says find the measure of angle T. All right, so if you look at those two angles, so again, I'm going to color code. All right, so I'm going to look at this angle T is inscribed to this arc of SV. And then I have that this angle of U is also inscribed to that same arc of SV, which means that these two angles right here have to be congruent. So to solve, I'm going to set 3x minus 5 equal to 2x plus 15. I'm going to subtract out the 2, so I'm going to get x minus 5 is equal to 15, which means that x is equal to 20. And so it's asking us to find the measure of angle T, so I'm going to take that 20 and I'm going to plug it in. So the measure of angle T, the expression is 3x minus 5. I'm going to take that 20 and plug it in. So I'm going to do 3 times 20 minus 5. I'm going to do 60 minus 5, all right, which means that the measure of angle T is 55 degrees. All right. So my next theorem says that an inscribed angle of a circle intercepts a semicircle if and only if the angle is right. Okay, so one more time. An inscribed angle of a circle intercepts a semicircle if and only if the angle is right. So if I come over to this picture that I already have for you, okay, what I want you to look at, and this should conceptually make sense to us, okay? We shouldn't actually really need a theorem for this. So what I want you to look at is this angle of FGH. And so what we have is we have this angle that's inscribed to this semicircle right here. So the endpoints of that angle lie on the diameter. And this should make sense to us because the measure of the semicircle is 180 degrees. And we know if an angle is inscribed to that, it has to be 90 degrees. Okay? So essentially, if you ever see like a triangle that has this segment as its diameter, then it has to be a right triangle. Okay? So if you ever have a triangle that's inscribed in the circle and the one side is the diameter, it has to be a right angle. So an inscribed angle of a circle intercepts the semicircle if and only if it is a right angle. All All right, so our last two theorems here, and then I'll pause, and then we can go over some application of this. So if you look here, an inscribed polygon, we have actually already talked about this before, okay? We've actually gone over this theorem before. So it's if each of the vertices lies on the circle, all right? So an inscribed polygon happens if each of the vertices lie on the circle. So if I would go ahead and draw that real quick, all right, if I would draw my circle, and let's say I just want to inscribe a triangle, all three vertices would have to lie on that triangle. So that would be an inscribed triangle. So this is an important topic before we get into this last theorem, because this last theorem says if a quadrilateral is inscribed in a circle, so if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So then its opposite angles are supplementary. So if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Okay, so example 3 says, which two pairs of angles are supplementary? So what I have here is I have a quadrilateral that's inscribed inside the circle, and what we know is that the opposite angles have to be supplementary. So looking at angle L right here, okay, angle N is going to be supplementary. So angle L and angle N are a good example of supplementary angles. Okay, we do have one more set. We can look at angle K and angle M. Those are opposite angles as well. So angle K and angle M. Okay, so I'm going to pause here, and then we're going to work through these examples, and we'll go from there.